Hi, welcome back to Chem with Chem. In this session, we look at reactions of alkenes. As usual, at the end of the content section, we look at what we've learned by going through some past paper questions. So this time we have not one, not two, but all of three past paper questions just to concretize your learning. If this is your first time to the channel, be sure to like if you find value, share with a friend or two, and of course, consider subscribing. You do not want to miss out when new content is added. It's not too late to book a session with ChemwithKem. You can do so by sending an email to chemwithkem@gmail.com. All the best. So just to start off, alkenes undergo combustion reactions. We get carbon dioxide, water vapor, and heat. Then they undergo addition reactions, and we can have many types of addition reaction depending on what is being added across the double bond. So you'll see the trend. So first we have, if we're adding hydrogen, we call that type of addition hydrogenation. Check it out. So we'd use nickel or platinum catalyst, and we would get, if we have the alkene, we would get the corresponding alkane from it. So if we start off with, for example, if we start off with ethene, we would end up with the corresponding alkane, which would be ethane. So here, this is ethene, and we're getting now ethane. So all we're doing here, we're cutting the carbon-carbon double bond. Let's show that. When we cut the carbon-carbon double bond, it means that we now free up space. The compound is no longer saturated. It can now accommodate. It can now accommodate another substance on it, another element on it. So we just put on two more hydrogen from over here, and we get the corresponding alkane. The other thing we can add is a halogen. So we could add bromine. When we add bromine, they could be more specific and call it bromination. This is done, this could be aqueous bromine, that's bromine in the presence of water, or it could be bromine in a solvent, in an organic solvent, and this solvent here is tetrachloromethane. And we would get 1,2-dibromoethane, 1,2, to say that on carbon 1 there's a bromine, and on carbon 2 there's also a bromine. So there's a bromine on carbon 1, there's a bromine on carbon 2. So we say 1, 2, and because it's two of them, we say di. So we can add halogens, and that's called halogenation. Are we clear? Clear to move on from this one? We can add water, just like when we're thirsty, we drink water. We call that hydration. But when we add water, the conditions are a little more severe because we need to split the water molecule, a lot of things going on. So we would do this in the presence of phosphoric acid catalyst, which is in silica. We do it at 300 degrees Celsius and 70 atmosphere. And if we're adding water, what we're doing with us, as we said earlier, we're cutting the carbon-carbon double bond. We're going to put OH on one of the carbons, and we're going to put H on the other one. And we'd end up in this case with ethanol. So if we start out with ethene, we would get ethanol at the end of the day. So that's that addition of water as steam, and we end up with ethanol. And then there's what we call, if you look at the word, hydrohalogenation. It's adding what we call a hydrogen halide. That means hydrogen with a halide, like hydrogen chloride or hydrogen bromide. So the hydrogen would go on one of the carbons, and the halogen will go on the other carbon. So in this case, we end up with an iodine atom on the molecule. So this is iodoethane. If we had added HBr, what would be the name if we had added HBr? If it were HBr, we'd end up with, what would the name? Put it in the chat. If we had used HBr, if the hydrogen halide were HBr, what would be the name of the compound over the right-hand side, the product? So when it's HI, hydrogen iodide, we get iodoethane. What if it were HBr? What would we get? So it would have been bromoethane. Very good. All right. So the last two reactions we have, when we have, we can use acidified potassium manganate 7. That's a very powerful oxidizing agent. It has a lot of oxygen to donate. So we're adding acidified, or what we're really adding is 2OH group. But when we add oxygen to the whole mix, that's called oxidation. So we really would be oxidizing it in a sense. So the oxygen comes from the oxidizing agent. So we don't need to, all we need to do is just put the O in bracket there along with water. But it's not just a regular alcohol we get a special alcohol. This alcohol is called a diol because it has 2OH group. Di means two, and al coming from the alcohol group. So this would actually be called, to be more specific, this would actually be called ethane 1,2,1,2-diol. And this they use in antifreeze, or they use it to make coolant. It's a special type of alcohol. And then the last one is polymerization, which we're going to be looking at a little later on. That's why there's an asterisk there, so we can give it its own time. So when ethene is heated to 200 degrees Celsius at high pressure, around 2,000 atmospheres rather, or even at low pressure, 25 atmosphere, and a suitable catalyst, we get polythene. And that's, we know that more popularly as polythene, the bags, the plastic bags, the poly bags that we use when we're making sip for sports day, or mix up Gatorade and put it in there, or you buy gummy bear in them. So those little plastic bags is a result of reactions of our alkene. So we can put many alkene molecules together. And all we're doing here, we're cutting the carbon-carbon double bond. We're cutting one of them. And when we cut it, this is what would pretty much be happening. You cut it and you now make an available space ready to be used. So if you cut it, it means this part can be tied on to this part over here, and this part can be tied on to another part. So what we'd actually get over here is a continuation. All right, and you can sometimes see that a little curly line right there to say that that's just a portion, so that could continue. Or as it's written there, you see a bracket with an N outside. N can be 50 or more. So that's showing a partial structure of the ethene molecule. So this would be ethene and ethene going together to give us polythene. Poly means many, and ethene coming from the ethene molecule. So this will be explored a little later on. So we're gonna, with this part done, we're gonna delve into a few past paper questions so we can get some more practice. The question we're working is January 2019, question 3. Compound A is a straight chain hydrocarbon with the molecular formula C5H12. So it's telling you how many atoms of carbon you have and how many atoms of hydrogen you have. They're asking you now in part 1 of 3A. State one natural source of hydrocarbons and two possible uses of compound A. Now, you really need to know what compound A is. What's compound A before we even give the uses? So we know the sources. Let's knock off the sources. Sources of hydrocarbons, what would that be? So natural gas, coal Coal isn't the best one. Coal isn't the best answer. We're looking for crude oil or petroleum. Coal. Coal. You would not find you use coal as fuel, but you would not find hydrocarbons in coal. All right, coal is considered carbon, just carbon that is burned, used as a fuel. But the answers here: natural gas, crude oil, and if you even put peat, you could get it. But the two main answers are natural gas and crude oil. Crude oil is also known as petroleum. All right, so they're asking for the use of this compound here, C5H10. What's the name of that compound before we go any further? Because to name it is to know what we use it for.
Pentane.
Pentane. So pentane means it's what family is that from? If it's pentane.
Alkane.
All right, so from the alkane family. So what do we use it for? It's a fifth one. So most of them are used as fuel. So that's one thing that pentane is used for. What else could we use pentane for? So I'll give you a few seconds to think about it.
As a solvent.
As a solvent, as long as you don't say to drink. So as a solvent, so they are used to dissolve non-polar substances. So we can use pentane as a fuel, it burns, and we can use it as a solvent. And here they want us to draw the fully displayed structure of compound A. Note what's important in the drawing. 5 carbons, and they must all be taking part in no more than 4 bonds. Once we have that, we're good. That's what it looks like. Draw with me. So if I draw it, you should draw it. They're asking us, they said thermal and catalytic cracking are very useful processes in the petrochemical industry. Define the term catalytic cracking. 2 marks. What is catalytic cracking? The name kind of gives it away. They say catalytic and they say cracking. What happens in cracking? So it's cracking, but you're using a catalyst, but you cannot use but the word cracking.
It's like the breaking of long hydrocarbon chains into smaller, more useful ones using a catalyst.
All right. When you answer it like that, you're going to answer the other part that they're asking you in part 2. So we'll say it's the breaking of long chain hydrocarbons into smaller ones using a catalyst. And the importance is that catalytic cracking yields more useful products. So the long chain hydrocarbons, there is very little you can do with them. They don't burn as well. They're not as combustible. So we'd have only crack them into smaller chain. Now it's easier for those to burn. Just like our refinery gas ignites better than gasoline, which ignites better than kerosene, which burns and ignites better than diesel, which burns and ignites better than heavy fuel oil, and so on. And we also get smaller products that can be used as precursors for other reactions. All right, so that's that. Let's look at the other part. So they're saying no, this should be, we're gonna fix that. That's C5H10. Another hydrocarbon compound B with the formula C5H10 can be converted to compound A in a simple one-step reaction. Draw a fully displayed structural formula. of compound B. So compound B has the formula C5H10. What kind of compound is this? What family is it from? Or what's its name?
Pentene.
Pentene, all right. So we can just put on the carbon double bond on the first carbon. 3, 4, 5. Pentene it is. That carbon double bond could have been at the second carbon as well. So that's pentene. Let's see what else they're asking us about pentene. State one physical property of both compound A and compound B. Each of you can give one physical property. So we have pentane and pentene. So this we said is pentene, but they asked us about pentane earlier. C5H12, and this one is C5H10. What's a physical property that's common to both of them?
So they don't dissolve in water.
All right, so they don't dissolve in water. What else? What about their physical state at room temperature? What are they? Would they be liquids? Would they be gases? Would they be solids? So this is correct. They don't dissolve in water. What else? Solids, we're talking about 5 carbons long. You don't get solids until you reach like about, say, 15 or so. Liquids, so there would be liquids
Oh,
at room
okay, sir.
temperature. So there are liquids at room temperature and pressure. So those any of those two would work. You could say that they have low, you could also say they have low melting and boiling point. All right, so those could work. Liquids, right, indeed. Compound, what they meant to say right here, compound A and compound B can be distinguished by reacting them with bromine solution in the dark. State which of the two compounds, A or B, reacts with bromine. So in this case, they're talking about reaction of compounds A, compound A or B in the dark. Which of them will react with bromine, A or B? So we're talking about pentane versus pentene.
Sir, would it be B?
Compound B, all right, so B, it would be B. There's a carbon-carbon double bond, so that's one of the ways to distinguish between an alkane and an alkene. Bromine water or with bromine in an organic solvent known as tetrachloromethane CCl4. What's the color change that would observe?
Brown to colorless.
All right, you're on a roll. Brown to colorless. And they want a balanced equation, so that would be C5H10, which is a liquid, plus Br2, which is also a liquid. Liquid going to be in tetrachloromethane CCl4, and that will give us C5H10 Br2, which is the liquid. And we'll get 2 marks. We'll get 2 marks for that. So that would be that. And that would be it for 15 marks. That would be it. So we'll continue down the line. All right, so let's look at this one now. This one is the same year, but question 5. Compound D, and they give the condensed formula. There's a CH3, a CH2, a CH2, then COOH. It has a very unpleasant smell and a bitter taste. They're asking for the homologous series to which compound the D belongs. They call this compound D. What kind of what homologous series does this one belong to? Are we seeing a functional group? Go ahead, type it up. We can assist by looking at the second part of the question. Structural formula and the name. That's how the atoms would be joined in space. So are we seeing the functional group? That wouldn't be an alcohol. The alcohol would be OH. If it were an alcohol, it would be OH. Wheel and come again, selector. So this time around, the group itself is this portion of the molecule. The part that has the COOH. So that would be actually be called the organic acids. Or if you give them alkanoic acids, that would give you the full marks. And they want the fully displayed structural formula. They want us to write its name. We're going to do its name. We have to count the number of carbons. The carbon here in the functional group is counted as a part of the chain. So that is 1, 2, 3, 4. So that's butanoic acid. And they would give you 2 marks for that. So it's an organic acid, butanoic acid. All right, let me know if we can move on to the next part.
For the first one, if you had a carboxylic acid, it would have been correct as well.
In fact, that's a better answer than organic acid. Carboxylic acid is a better answer. So we'll take carboxylic acid over organic acid. All right, carboxylic acid or alkanoic acid. So yes, you'd have gotten the mark right there. Okay?
Yes, sir. Thank you.
Cool. Compound D, that's butanoic acid that we just named, reacts with ethanol to form the sweet-smelling compound E. They want a balanced chemical equation for the reaction between compound D and ethanol. So compound D just now was C3, no, not C3. Let's take that again. It was C3, 2, 3, 6, and 1, 7, C3H7 COOH plus ethanol is C2H5OH. This is in aqueous medium. This is in aqueous medium. So when we have something like this, it's the acid part of it's the OH part from the acid going with the H part from the alcohol. We draw back the acid part first. I should have done them in color. So this is C3H7CO, then OC2H5 plus water. Gonna try to do it using the structural formula. All right, so this would be a liquid and this would be a liquid, and they would be separate. You can use a separating funnel to separate them. So this is what it would look like. We have something like this. 3, 4, C double bond O. Let's dress this up. So this is our butanoic acid. And then we're gonna go with the ethanol now. Do it in blue. So we're going to put the OH from the ethanol nearby. Two carbons. And it's the joining of the OH from the acid and the H from the alcohol. That comes off as water. So over this side now, we'd end up with, if you check it out, this is what it looks like. 1, 2, 3. The more you draw these, the better you become, the more it becomes natural for you. Then on the fourth carbon now, we have C double bond O. Then we have the blue part of the other molecule coming in, O, then C, H2 with a CH3. Hit them with a CH2 and a CH3 and a bang bang. 1, 2, 3. And then whenever I draw this, even when they don't ask, I normally highlight it to show the ester linkage. So this is an ester. So that's the ester linkage. I didn't ask for it, but since we're revising, that's the ester linkage. I'm going to take it off and do something better. I'm going to name it. When we're naming, when we draw the acid part first, but when we're naming, we name the alcohol part first and the acid part last. So this is 2 carbons long, the alcohol part, so it's ethyl. And that is, the acid part is 4 carbon long, so it's butanoate, ethyl butanoate. All right, so all of that is up here. This is what we need for the 2. I just expanded it using the structural formula so we can actually see how the thing is formed. Of course, we get water, H2O. All right, so condensation reaction means water is formed. Any questions? Of course, this guy here, we said is ethanol. Any questions?
No, sir, not present.
Cool, all right. Then they're asking us to suggest the conditions for the reaction between compound D and ethanol. What do we need? For 2 marks, we need to tell them everything that we need. We need 3 things. Need 1 condition from each of you. I would want to go first right here, so I'll give the easy one. So what do we need? The conditions we would put above the arrow, but we're gonna, since they asked us for it down here, we'll just give it. They just ask us for the balance equation. They're asking for the conditions now. That could have been included, but it probably would have been a little ambiguous or daunting. What are the conditions? I'll give you a clue.
Say, what do you need? Do you need heat?
All right, that's why I said I would want to go first. Would need heat. So heat is one thing we need. So we're going to heat the whole thing. All right, so both of the two compounds are in here. So we have the butanoic acid and the ethanol in here. Notice what is happening here. Well, H2O goes in at the top. This is a condenser. Right? Water comes out at the hot part, comes in at the cool part. Whatever we have that's been heated, when it evaporates or it starts to boil, the vapor goes up in the tube. But when it goes up in the tube and water, we know water is running through here. Water is in here. The tube is enclosed with a condenser where water is running. So when our vapor goes up here, our vapor cools and falls back down into the container. And the same thing keeps happening over and over. So what you actually have happening, it's like what happens in the stomach. You don't have the vapor coming out like in simple distillation. This we have it boiling, condensing, and boiling and condensing again. So we call that, there's a particular name we call that reflux. So it's in under reflux. So at the end of the day, you will get the product and the reactants being in the same container. All right, and the continuous boiling and the continuous cooling takes place. But then we also need an acid catalyst. We need like a few drops of sulfuric acid to catalyze it. So those three things: heat, reflux, and we need an acid catalyst. And then they ask us in part 3 to state the type of reaction that occurs between compound D and ethanol. Water is formed, so we call it a condensation reaction. If you give them esterification, I believe it could be accepted because it's an ester being formed. It's also a condensation reaction because water is formed. So either of the two would work. I think condensation would be a better response right there because water is formed. All right, cool. But it's not just cool, right? If you need to write. So we'll go with a condensation reaction here, because water is formed, so we can show them what we mean by that. Water is formed. And in order for us to get to the next part, we have to clean this part. They want us to write a balanced chemical equation for the reaction between compound D and the sodium metal. What's compound D? That's butanoic acid. And this is just revising the reactions of organic acids or carboxylic acids. They react similarly to our mineral acids. The only thing, let's clear this. The only difference is that where the metal goes. In your regular mineral acid, for example, hydrochloric acid, the replaceable hydrogen is at the front. So if we were to react this with sodium, as explosive as that would be, we would get the sodium taking the place of the hydrogen, and we get NaCl. Now, when we're using the organic acid, for example, we saw earlier that C3H7COOH. The replaceable hydrogen is at the end. If that's reacting with sodium, then when you actually get the salt, it's going to be C3H7COONA. It's going to the end. Then we end up with hydrogen gas. And to balance everything, we would need two of that. Are we getting somewhere? Because we cannot just have H2, hydrogen exists as H2, so we need 2 of the butanoic acid. If we need 2 of the butanoic acid, then it means that we need 2 of all of that part right here, and then that would make us need 2 sodium. And then it's hydrogen gas that's present. Look at the many things that they're testing from one question. Describe one test that could be used to identify the gas. How do we hydrogen? How do we identify? How do we identify hydrogen gas? What do we do? Note the salt, sodium butanoate. Coming back to that gas thing. Burning splint. So we test with a lighted splint. 1 mark for that. 1 mark for telling what we'd observe. So what does the gas do? The gas puts it out with what? So we use a lighted splint, and the presence of hydrogen is marked by the flame being extinguished with a popping sound. With a popping sound. Depending on how much gas is being produced, you might get a squeaky pop, but the more gas is produced, the bigger the pop is. And this happens because hydrogen is really explosive. And they're asking us now to state whether the salt formed will be soluble in water. Let's look back at the salt. Sodium butanoate. They're asking us to state if the salt formed, if it's soluble in water. Give a reason for your answer. Put this in the chat. Is it soluble? Soluble or insoluble? Soluble in water. Sodium butanoate. Soluble, one person says yes. Get your reason ready. Cue up your reason. What about the rest of us? Not sure? Still need a response, even if it's not sure. And even if it's a salt that you've never seen before. So we're gonna say yes, it is soluble. Okay, go ahead. So what's your answer?
Sir, I was saying yes.
Okay, so why is it soluble?
Sir, because all salts with Na. Oh God. Sir, like I know the answer, but I can't explain it right now.
No, man, that's right, man. All sodium salts, all salts of, not all sorts, all salts of sodium. While we're at it, all sodium, ammonium, and potassium salts are soluble. All these salts are soluble. So that would give you the 2 marks to top it up to 15. All right. Let's see what the future holds down here. Wait, I forgot to ask you. So May 2018, we're going back in. Compounds X and Y are simple hydrocarbons. Compound X has the general formula CnH2n plus 2. CnH2n plus 2 with N equal 4. And compound Y has the general formula CnH2n with N equals 3. State the homologous series to which each compound belongs. Okay, compound X. N equals 4 coming from CnH2n plus 2. Group, which homologous series is that? Whatever N is the number, whatever the value for N is, which represents the number of carbon atoms. For hydrogen, it's twice that plus 2. Which group is this?
Say, alkene.
Alkane. Thank you, sir. Why?
Sir, it's alkene.
Alkene. State one use of each of compound X and compound Y. The one with X, homologous series, N equal 4 is for the first one. So they say N equal 4. So it's that one, 1, 2, 3, 4. Okay, cool. And then the other one N equal 3. Okay, one use for the first alkane that the compound X can be used as a fuel. All right, cool. Can't go wrong with fuel. Well, most times. What about compound Y now? N equal 3. N equals 3 for compound Y. For the drawing, I'll do the drawing. So the alkane, N equals 4. 1, 2, 3, 4. We know how to name them. 1, 2, 3, 4. Meth, et, prop, bute. And you said it was an alkane. So that one would be called butane. What do we use butane for? No, we did that already. So we passed that one. So we know at the alkene is N equals 3. 1, 2, 3. Meth, eth. So meth is for 1 carbon. Eth is for 2 carbons. Prop is when we have 3. Bute is when we have 4. All right, so this is N equals 3. So we're looking at, what's the alkene right here? And you won't get away with saying fuel. We have to give something a little more specific than that. Even though it can burn, but the alkanes would be used preferably as fuel than the alkenes, even though they can burn. So this one, N equals 3, so it's propene. And we're just writing out those in somewhere on the page to help us with the answer. What do we use propene to do? We haven't delved into it as much. We looked at an example earlier when we can join, where we saw us joining many ethene molecules to give you polythene. But we could do something similar. We could join many propene molecules and give us polypropene, which is used to make, used to make polypropene, which is a type of plastic, it's a type of polymer. Used to make the polypropene polymer. All right, so it's a precursor, a starting material for that reaction. They want the fully displayed structure of compound X and Y. So butane is 1, 2, 3, 4 carbons. Many see organic chemistry as a break from moles with all of those calculations. They just need to know a few rules that they're governed by. They draw the compounds, ensuring carbon is not taking part in any more than 4 bonds. And then the other part, at all times, carbon not taking part in more than 4 bonds. Let's ensure that that's the case. It's tempting to dress up the other part, but it's 4 in all cases. That's our carbon-carbon double bond. So we have butane and propene. Compound Y reacts with water to form an alcohol. And we say compound Y just now was propene. Was it? Yes, compound Y is propene. It reacts with water to form an alcohol. They want the structure of the alcohol. So all we would do in a case like this, we would just, not just, but we would cut the carbon-carbon double bond, get the water, cut it into OH and into H, put H on one carbon and put OH on the other one. So we end up with our alcohol. See, 3 of them. We can decide where we put it. Let's do it in red. And this would be the reagents and the conditions necessary. We looked at that a little earlier. Let me see if I can pop it back up. Hydration. We can add water. We can add water in the form of steam to our alkene. We would need phosphoric acid catalyst, 300 degrees Celsius and 70 atmospheres. So that's phosphoric acid catalyst in silica and 300 degrees Celsius, 70 atmospheres. So the reagents would be H3PO4 in silica, condition 300 degrees Celsius and 70 atmospheres. 1 mark each. That would give us our full marks. In the next part, they're saying ethanol reacts with ethanoic acid to produce a sweet-smelling oily liquid. Whenever you hear that sweet-smelling, you can think of the word ester. They said it, an ester. The name of the ester, well, it's ethanol, so you'll get ethyl for that part, and it's ethanoic acid, so you get ethanoate for that part. So it's ethyl ethanoate. They want the full equation, so we can just give them that CH3COOH aqueous plus C2H5OH. Alcohol, you could aqueous as well. And this would give us CH3COOC2H5 plus water. And that would give us our full marks. Key thing to note, whenever we're working with an ester, we draw the acid part first. But we named, well, in this case, it doesn't matter how we name it because they're both 2 carbons long. But we draw the acid part first, or we write the acid part first and the alcohol part last. And just like that, we've come to the end of another successful session. I sure hope that you found value in this. Be sure to check out all the other content that we have. I don't think you can exhaust the content that's on the channel, but look at all the other reactions of the different homologous series along with the past paper questions to concretize your learning. Of course, if you found value, leave a like, leave a comment, and please share with a friend. Couple later.